Hey guys, in this video I will be showing you how to build an Arduino controlled RC hovercraft. Let's get started by talking about some of the major components that I used in this build. To create the lift, I'm going to use this 12 volt CPU fan that I bought on eBay for $5. For propulsion, I'm using quadcopter replacement motors and propellers. For the brains, we'll use an Arduino Uno. Here we have a 9G micro servo for controlling the steering. I will use an RC transmitter and receiver to talk to the Arduino and to control the servo. For the body, I have a 5mm piece of foam board, and for the skirt, I have some heavy-duty trash bags. For controlling the speed of the propellers, I'm going to use two L298N motor control boards. For power, I have a 3-cell LiPo battery, and I've changed the end connector to an XT60 so I can build a custom cable. In building the custom cables, I'm going to use some heavy gauge wire to feed the L298N motor control boards, but I also want to feed a line to the Arduino to keep track of the battery voltage. There are two reasons to keep track of the battery voltage. The first is that we don't want this battery to discharge too far, so when it gets below 11 volts, I can have the Arduino put the hovercraft in low power mode. The second reason has to do with these propeller motors, which are only rated to 3.7 volts. We'll use our software to make sure that we don't send too much power to the propellers by pulse width modulating the power coming from the L298N. Now this battery fully charged will put out 12.6 volts. The Arduino, however, is only capable of measuring 5 volt analog input. So we're going to use these resistors to build a voltage divider so that we don't overpower our Arduino. The black and red wires will be the main power, positive and negative. This black and this red will go to the Arduino, and we'll use two 10 kilo ohm resistors in series connected to the positive side, one 10 kilo ohm resistor connected to the negative side. This setup will deliver 1/3 of the battery voltage to the analog input pin on the Arduino. Here I've soldered the two 10 kilo ohm resistors together and wrapped them around the lead wire, and they will solder into the positive terminal on the XT60 connector. And now a very similar setup for the negative side. Finally, I've taken the analog input wire and connected it to the two resistors from the positive and negative side. And now I'm going to test out the voltage divider. First we're going to test the battery voltage, and we are at 12.5 volts. Now we'll test with the new cable. That in, and as expected we're reading 4.1 volts, about 1/3 of the battery voltage. So I'm going to write these two numbers down, 12.5 and 4.1. We will use those again in our Arduino code. The L298N is one of my favorite boards. I use it in many of my projects. It's very powerful, it's very inexpensive, but it does have some limitations. Each board can control two motors, one on each side, and is capable of providing 2 amps steady state or 3 amps peak to each motor. Since each of the 4 motors requires 2.5 amps, I'm going to need both boards, both channels on each board. Normally, to drive 4 motors, you would need 8 separate inputs from the Arduino. Because all 4 motors will be turning in the same direction and at the same speeds, I will only need one PWM input from the Arduino. In order to do this, I did make a few modifications to the board. First, I've jumpered inputs 1 and 4 together, and I've shorted inputs 2 and 3 to ground. I've also connected the outputs 2 and 3 together, outputs 1 and 4 together. By daisy chaining in this manner, I'll be able to power all 4 propeller motors at the same time and use only one PWM command from the Arduino. Now the code for this project is not too complicated. First of all, we need to declare a few integers. We're going to have Arduino pin 7 connected to the RC receiver channel 2, which corresponds with the throttle on the transmitter. And pin 8 on the Arduino will connect to RC channel 3, which corresponds to a push button on the transmitter. Although you can control the servo with the Arduino, I decided not to. Instead, I'm directly connecting it to channel 1 on my RC receiver. Now, pins 10 and 11 will be outputs from the Arduino, Pin 10 will connect to the in1 connection on one of the L298Ns, and pin 11 will connect to the MOSFET as demonstrated in my previous video on fan control. The RC receiver will provide a pulse width between 1000 and 2000 milliseconds, so we'll use these two integers to keep track of the commands coming from the RC transmitter. This integer will be used to prevent the quadcopter motors from receiving too high of a voltage. This one will keep track of the LiPo battery voltage, and this one will be used to control the speed of the propellers. Here in the setup loop, we will declare our pins as inputs and outputs. We'll make sure that the fan starts in the off position, as well as the props that they're not spinning. Okay, first thing here in the loop, we will measure the fan pulse width from the RC receiver, and if that width is less than 1500, we will make sure the fan is turned off. If it's greater than 1500, we will turn the fan on. I'm using analog channel 0 to measure the battery voltage, but because we're using a voltage divider, we need to multiply this value by the ratio of the two voltages that we measured earlier, 12.5 and 4.1. This will give us our actual battery voltage. We will use this battery voltage to scale the PWM signal so that the quadcopter motors never receive more than 3.7 volts. When the battery voltage is high, we will send it a smaller PWM value. When the battery voltage decreases, we will increase that PWM value. If the battery voltage goes below 11 volts, the user will notice a significant drop in power as we are cutting the maximum power in half. Now for the propeller control. With my unit, a pulse value of 1000 milliseconds would correspond to full reverse, and a value of 2000 would correspond to full ahead. 1500 is the neutral position. These propellers only spin in one direction, so for reverse values, we want to ignore them and simply write an analog value of 0. For values in the forward direction, we will map those between 10% power, or PWM of 25, and our maximum calculated power. Then we will write those values to the pin that connects to the L298N. You'll notice that this loop does not have any sort of time delay. We are okay running this as fast as the Arduino will go. Now I definitely want to test these before plugging it into the propeller motors. So instead of hooking it up to the battery, I've got my power supply here, and it's set to 12.6 volts, which represents a fully charged battery. And if you watch the multimeter as I squeeze the trigger here, we'll measure the output of the L298N motor control board. So here I am squeezing the trigger. We've got 2 volts. If I squeeze it all the way, looks like 3.9, which is close to what we wanted. Now you'll notice if I turn the voltage down to say 11.2, squeeze the trigger again, we still get 3.9 volts. So the software seems to be working great. Now let's try a low battery condition, 10.8 volts, which is below the 11 volt cutoff in our code. You'll notice now when I squeeze the trigger, we're only getting 2.2 volts. So the software is working. It is reducing the voltage going to the propeller motors when the battery is in a low voltage condition. Now I'll see if I can turn the fan off and on using the remote control through the software. To do this, I've connected a MOSFET both to the fan and to the Arduino output pin. For more details on how to do this, check out my other video on Arduino fan control. Once again, I'm going to fire up the power supply, and this button right here corresponds to channel 3 on this remote. Push it, fan comes on. Push it again, turns off. Looks like it's working great. This is a piece of Ross foam board that I picked up at Walmart for about 80 cents. And the first thing I'm going to do is cut a rectangle about 20 inches by 14 inches. Next, I'm going to round the corners. Next, I'm going to mark a center line on this and mark out where the fan's going to be. I'm going to put it about 4 inches from the edge. Before I get too far on the body, I need to lay out the skirt. So I'm going to mark a line 11 inches all the way around the body. Now before I take this off, I'm going to do a quick outline so that I know where to place this again later on when we go to mount the bag. Okay, with that marked, I can remove it. I'm going to be cutting a 4-inch wide path for the air to escape, and I'll be reinforcing that with duct tape. In order to contain all the electronics, I've cut these pieces of foam board that I'm going to attach to the side using super glue. I didn't measure anything, just cut it kind of to fit. I also made this piece here to hold the servo that will support 2 of the propellers. Now for a couple coats of paint. Next, you'll want to lay down the plastic with the duct tape side down and recenter the hovercraft in the center of the bag. I'm going to be folding this bag over and running a little piece of tape all the way around the edges. Next, I'm going to install the fan and propellers using super glue, and the rest of the electronic components using tape. I'm using tape for those because I may have to move them around a little bit later on to get the center of gravity just right. Everything is plugged in. Let's turn on the transmitter. See what happens. We give the trigger a little squeeze. Looks like the propellers are working. We have steering. And now to test the fan. All right, everything seems to be functioning. Let's go test it out. Okay, so right off the bat, I noticed that I have a problem when I hit the propellers. Hovercraft doesn't move. What I think is going on is that this design is creating too good of a seal with the ground. In a previous attempt, I used this 2-layer design, which seemed to work much better. I think it has to do with having a flat plate here at the bottom. So I'm going to make a modification to Big Red here and see if we can make him glide like this last one did. Well, the good news is that garbage bags are really cheap and I can easily repeat this process. I'm going to use this piece, which is about 2 inches smaller in each dimension than the hovercraft itself. I'm going to tape the bag to this piece here, then glue this piece down again and repeat the taping process. Hopefully it works a little better this time. Alright, so I reattached this. I actually trimmed about 3 inches of this garbage bag off because I still wasn't able to move the hovercraft. Then I finally realized that I had these blades switched so that the rear and front propellers were opposing each other. So now that everything's put back together, she's gliding and flying. So overall, I was very pleased with how this thing would glide across the floor. It means the lift fan was doing its job. These little propellers, however, didn't quite do it for me, so I think in the next version, we're going to have to get a little bigger. In fact, for version 2, I've got a larger propeller and motor, brushless motor controller, and a larger battery. All this means that it'll be a little bit heavier, so we'll need a little bigger base and a bigger fan. And for that, I purchased this 4-wire fan that's puts out about twice as much air as the fan I used in this version. I've got some different ideas for the next design, and the hope is that I can take it out on the lake and have it drive across the water. So keep your eyes open for that video, and once again, thanks for watching.